So last lecture we talked about the FinFET-based SRAM design. And here are some images from Intel's 22 nanometer SRAM family. So, for different levels of cache, you may have different designs. So here you have the high density cell and standard cell and high speed cell. So basically you trade off between the area and then the speed. So here from this microscopic image, you should be able to tell what is the ratio between the pull down, cascade, and the pull up, right? So because the SRAM layout follow a very similar design, even for different technology nodes. So you have seen this many times before. And you have question?
Yeah, for the standard cell, is there a mismatch between the cascades on both nodes, or is that something else? Because it seems on one there's double width, on one it's just single width.
So the image is not very clear. So I think there is a one cascade here, right?
But for the standard cell.
For the standard cell. Oh, you mean here?
Yeah.
For the standard cell, let me see. So here you have the one cascade, right? And then two, not cascade, one pull up. And then two pull down, right? So here, I think this is not very clear. But I think this one is one, right? So you mean the other side?
Yeah.
Okay, so then let's see. So here you have pull up, and here you have two pull down. I mean this one, right? A little bit. So I think there's an resolution problem, and also maybe it's a dummy fin. Actually, there's no actual fin underneath, so there may be a dummy. Yeah. So this is a 3, 1, right? So here is 111 high density cell. Not 3, I mean 221. Sorry. 211. And this is 3, 2, 1. Okay. So then here this is a Shimon plot, and then you have the trade-off between the clock speed and then the power supply voltage, right? Okay, so then let's move on. So here then this is the second generation, which is a 14 nanometer FinFET. And you see the scanning. So the SRAM cell area almost become 50%. And then here we show the cross-sectional image of the FinFET. So you see here the difference from 22 to 14 nanometer. So what is changed here? You notice that here the fin becomes thinner and taller. Okay, so this is a general trend. So here we summarize some typical numbers. Of course, different foundries may have a little bit different design, but this is a general dimensions. Let's say from 22 nanometer down to 7 nanometer, your fin height, the height of the fin become higher and higher. And then the fin width become a little bit smaller. Of course, it's very thin already, like only a few nanometers, so you cannot really shrink too much. But the key point is that the fin height become larger, and also the fin pitch, that is the distance from the fin to fin, right? This is a pitch, also becomes smaller. So this is how you improve the density and also improve the current. per footprint, right? Because now you know the FinFET effective W is the height, twice of the height plus the fin width. So the height is increasing. So each fin is giving you more current. So that's the general trend. So any questions here? Okay. So here again, this is another image for the high density S1 cell and high performance S1 cell. And you can tell that always the high density cell is always 111, right? 111. And then in this case, you can see this is like a 221 for this high performance cell. Okay, you can do this exercise by yourself. And this is another design. And you can look at the ratio again. So this is the 10 nanometer node. And then the cell size shrink to about 0.05 micrometer square. And then here at ICC 2016, Samsung reported a 128 megabit SRAM macro with 10 nanometer FinFET. And then high density cell is about 0.04 micrometer square. So here, this is like a design rule. For high density is always 111, and then the high current is 221. So the order is reversed, but it's pull down 2, cascade 2, and pull up 1. So here the SRAM cell area, let's say, keep scaling to about 0.04 micrometer square at 10 nanometer node. So this trend continues, right? So then TSMC has this 7 nanometer SRAM. And here are some reverse engineering reports by looking at the caches in the iPhone. And then here are the dimensions. So yeah, you can see that this become very thin and tall, right? As we discussed earlier, the FinFETs, the fin become very thin and tall. And here is the 5 nanometer cross section. So here one difference is that for the PMOS, TSMC introduced the silicon germanium channel to further boost the hole mobility. So it's not pure silicon. So this fin is made of silicon germanium, like alloy for the PMOS. Okay, NMOS is still silicon. So here, let's revisit the variation. So here, this is what we briefly mentioned before. So for FinFET, the RDF is insignificant because the fin is very small dimension there, and it's almost undoped. Okay. Then the non-edge roughness and the work function variation will become the dominant factor. Especially here, the fin edge roughness, right? The fin is like very thin. So if you have any like variation, then that will also give you a lot of surface scattering, and then the transistor characteristics will spread out between different transistors. And if you use that to build your SRAM, so here you will have this kind of SNM distribution, right? And then also you can consider local variation and global variation. Local variation means you only look at within the array, And global, you need to look at from die to die. So of course, global will be larger because you have the differences from larger distances. So here, this is a summary for different companies, and their like SRAM cell size. So here, and also their FinFET design dimensions, like the pitch and the CPP, and then the CPP and metal one pitch for the FinFET. So it starts slowing down, right? You see that. So we will talk about how to extend this scaling in the next few slides. So here, as we see the slowing down of the FinFET scaling, then the industry started thinking whether we should change the device structure again. And this was a proposal to change from the FinFET to the gate-all-around nanosheet. So GAA stands for gate-all-around. Okay. So here then this is a cross-sectional view, right? FinFET, if you rotate by 90 degrees and then stack the channel horizontally like this, but then you now surround the channel with the gate that is all over the four sides. Then this is like gate all around. Okay. So this will help you to further boost the gate to channel coupling, right? Because now you cover this fully from four sides compared to the FinFET. Still the bottom side is connected to the bulk of the substrate. Now the channel is fully covered or surrounded by the gate. So you have the maximum gate to channel coupling that will help you to improve the electrostatic control that will help with the short channel effect. So this is a major motivation to change from the FinFET to the nanosheet. So any questions here? So FinFET, you can think of the phone, right? FinFET this way, and then you rotate, and then you stack, okay? So it's called stacked nanosheet, gate all around, stacked. Okay. So here, some additional features of the stacked nanosheet. Now you have some flexibility and also improved characteristics. For example, here, you can further increase the current. Why is that? Because you can stack many layers, right? The more the layers, the higher the current. So the current per footprint will be higher than FinFET. And also here, you can design the width with more flexibility, right? Because FinFET, you only have the integer number of fins. So the effective width is not very friendly to circuit designers. We discussed about this quantization effect before. But for the stack nanosheet, this width is still defined by the lithography. You can define the pattern. Of course, the effective W will be, right? For example, here, if you think this is the coefficient DNS nanosheet width or dimensions, and then you have the thickness, right? Each will be like D plus T times 2, right? That give you four sides, and then multiply by the number of the layers, right? So you can choose the D by the lithography. Therefore, this effective W could be more continuously tunable. Okay. So for example here, right, you have three like logic cells. Then for high performance cell, you can make the width, this width larger compared to here. For example, you can have the width 45 nanometer compared to here 15 nanometer, which is narrower. And for SRAM, you can also change, right? For different pull down and pull up, you can tune this differently. So any questions here?
Quantization effect in FinFET, it was twice of fin height plus thickness of fin, right?
Mm-hmm.
So are those both fixed? Like can't we make it flexible using lithography? Is it fixed for a technology?
It's fixed for the technology because the fin height is not so easy because that fin height, I mean, will be the same across different locations of the wafer, right? So that fin height, of course, you can say that your fin height could be a bit different, right? You say from 10 nanometer to 7 nanometer, then the fin height will be a bit different. But then for the same technology node, then the fin height is fixed. Therefore, you only have the quantized version of that, right? As a circuit designer, you cannot change that. But here, you can change that because this width is defined by the lithography, and then you can draw the layout with different widths, right? I mean, this width, this nanosheet width. Okay. So here are some more details on how to fabricate this stack nanosheet. So it's complicated, but I just want to give you some high-level overview. So the key here, the very important key for the fabrication is the first step, silicon germanium and silicon epitaxial growth. This is the key, okay? So what is this? So because this channel is something on top of the silicon substrate, right? You have to regrow this channel. It's not from your substrate. You have to build something on top. So this process is called an epitaxy. You add something on top, okay? So from the silicon substrate, you first need to grow the silicon germanium, which is this darker layer. And then you have the silicon and silicon germanium and silicon. You repeat this, okay? Depending on how many layers you may need. People have demonstrated dozens of layers. You can do this repeatedly. And then the second step is to still pattern this. Okay, you etch. Okay, you etch. And then to make this like still like a fin, because you still need to split. Right from the layout here, you have to split. And for example, the here this part and this part, you have to split. Okay. Oops. So you cut and split. And then you will have some dummy gate patterning. You will cover this. It's like a fin. If you think about this, this is like a FinFET fin. But then it's not like pure silicon. Actually, you have the channel like this built in like this. And then you have the dummy gates. After that, what you need to do is and then you have this like spacer and so on, those kind of dielectric in between. So then what is important is this step, channel release. Okay. This step is to have some chemical to etch the, let me see, where is that? Okay, here. To etch the silicon germanium in between. So you want to release the channel. So in other words, let me show you something, maybe. So you have this silicon germanium stack, right? So in this channel release step, you're going to have some chemical to attack the silicon germanium layer and then remove this layer. So this will be gone. So your silicon will be standing there, like really standing there. Of course, you have the source and drain and then those like mechanical support. But within the channel, underneath between the two silicon channels, this will be like a void. Okay. After you remove the silicon germanium. And then you do this real gate stack, regrow. Here you are going to regrow your like a gate stack surrounding the silicon. Okay. And then you get the metal gate in between. So finally, you get this kind of cross-sectional view. So here the source and drain is in and out of the plane. So we are looking at the cross-section, the nanosheet, right? We are looking into this nanosheet from this set of view. Okay, so here, any questions? Yes or no, this is still active research. In the initial versions, no. But then if you read the latest paper, still people claim that you want to have some silicon germanium for the PMOS. So they do so-called cladding. So still this bridge needs to be silicon. But then the silicon germanium could be, surrounding the silicon a little bit. Okay. Or you do the release, you do not fully release the silicon germanium, something like that. It's a sacrificial layer. That's a good question. I think it's because of this epitaxial growth. And yes, it's similar to silicon. And then you can, have the lattice like a match. And then also the chemical solution, attack the silicon germanium rather than the silicon, then you can have this release process. Question? Not MBE. It's not MBE for sure. It's just I don't know the exact process. There's epitaxial machine to do this job. It's not MBE. MBE is too slow for industry. They just sell this as an epitaxial machine from those equipment vendors. Okay. So here then there are some new challenges in this gate-all-around nanosheet design. One of that is the work function engineering become more difficult. Why is that? Okay. So if you recall, we talk about the high-k metal gates and then the multi-work function engineering by changing the, the high-k metal gate, right? You can have different heights of the metal gates, or you can have like different materials in the metal gates. But here, since the space is very tight between silicon germanium, and this space actually is fixed, so you cannot play with this different heights of the metal gate to change the work function, because between two silicon channel, right? You have silicon channel. After your release, you have some void here, and you regrow your metal gate here. So this distance is fixed. So you cannot have the thickness to have different VTH. So then this is one challenge, okay? The second challenge is, again, the PMOS. We just talked about this, right? So PMOS mobility will degrade. The reason is that for the silicon nanosheet, because of silicon orientation, this in the channel direction is 110. This favors the electron mobility, but then it will decrease the hole's mobility. This is unlike FinFET. FinFET along this direction could be 110. So there are still challenges in the nanosheet design. This is still active research. It's not finalized in the industry. So only Samsung has a product right now, as of today, I mean. And then TSMC and Intel has not really fully transitioned to the nanosheet. Of course, it's on their roadmap. They say maybe next year they will have that. But as of today, it's not there yet. Okay. So another innovation moving forward is the backside power delivery of this BSPDN. So if you look at the entire stack of the technology in the front end and back end processes. So what do you have traditionally is the silicon substrate, and then you have your transistor in the very first layer, and then this is the FEOL front end process, and then you may have like a 15 or 16 layers of metal routing. Right? This is called the back end of the LAN process, BEOL. So this metal routing has two purposes. One is to conduct your signal, right? Including the clock distribution. But then at the very top, like a few metal layers, is used for the power routing. You have your VDD and VSS, and then you need to power every gate, right? So then you have the very top metal used for the power routing. So a lot of congestions here already. So that's why we have like 15, 16, or even 17 metals for the routing. So the proposal for the future technology, for example, as Intel announced in their 18 angstrom technology node, of course, they are going to switch this to, as I said earlier, different companies have different names. Intel called ribbon FET, but basically it's a stack nanosheet. And then the key difference is that they're going to change the routing of the power to the backside of the silicon. And then they will have some connection from the backside to the front side. So if you look at the cross-sectional view, let's say traditionally, we have the FinFET, and then you have the VDD, VSS. Then this will come from the top metal, okay? And then the intermediate step is that they bury the VDD and VSS NAND, called BPR, buried power rail. But still, the VDD and VSS coming from the top, but then it's just buried into the silicon to locally power up this gate. And for the future, they want to move the entire power delivery network from the backside, and then they will have this nano TSV through silicon via. So they're going to dig a hole basically, and then refill this hole with metal, and then you can have this VDD coming from the backside of the wafer. So this will help with the standard cell height reduction a little bit, because you can hide some of those power rail to the backside. This will help shrink the cell height a little bit. Okay. So let me show you more illustrations here. This has already been demonstrated by IMEC and Intel. And other companies like Samsung, TSMC are also planning on this. So here, this is the nano TSV. It's a very small dimension, maybe 100 nanometer by 100 nanometer. It's a small hole into the silicon substrate. But first of all, the silicon substrate needs to be thinned down. Okay, this is the key. So this substrate will be thinned down to like a few micrometer scale. You know, silicon substrate used to be like 500 micrometer thick, right? If you have ever carried a silicon wafer, then the thickness of the wafer is typically like hundreds of micrometer thick. But in order for us to do this backside business, we have to thin down the silicon to like a micrometer, maybe 1 micrometer or a few micrometer in that dimension. And then you can do the backside like metal routing. So you can finish the front-end process, and then you flip the wafer, and then you do the metal deposition, dielectric deposition, and do the routing on the backside. But then, in order for you to connect the backside to the front side, you have to dig a hole through the silicon. And this is the TSV. And in this case, you need a very small TSV, a nano TSV, with like 100 nanometer in dimension. So you can collect this through. So here we show also the schematic for this design. Previously, you have this, let's say, power routing here. Now this power routing is moved to the back side. And then the silicon wafer used to be very thick. Now you have to thin down a little, thin down to very little dimension. And then you can grow the metal and dielectric on the back side for the power delivery. And usually power wires, you know, are large in dimensions because you have to drive a lot of currents, right? That's why in the traditional design, it's on the very top metal with very wide wire width. Now you move to the back side, then this is also wide. So that's why you see in this real image. So here, this is a silicon front end, very thin silicon, and you have whatever FinFET or stack nanosheet here. And then you have the top routing, the front side routing, and back side power delivery network. And you see it's very large in terms of the wire width. And typically nowadays they propose like the backside power delivery network, maybe 3 metal or 4 metal layers. Okay, any questions?
DSPs are connecting to the backside, right? How is the buried power rail helping? How is that connecting?
The buried power rail is not connecting to the backside. Okay, it's buried just for the VDD and VSS none. They're still provided. I mean, the power is still provided from the front side. So the true BPN will have the nano TSV from the backside. The BPR is like an intermediate step. So the ultimate goal is to have this backside power delivery directly attached to the back contact for the stack nanosheet. Let's say the source and drain will have the direct backside contact. Therefore, you can have the VDD and VSS powered in from the backside direct contact. This is not there yet. This backside contact, direct contact is not there yet. It's on the roadmap. Okay, so then there are new challenges for the backside power delivery. That is the thermal. Okay. So if you look at the traditional design, let's say we have the silicon. Actually, when you do the packaging, the silicon will be flipped facing down. Okay. So if you have a silicon die, then you will have the silicon die, let's say front end and back end process here. So this will be your silicon bulk. And then you have your transistors on this side. Okay. And then you have the back end of LAN, and then your pad here. So the die is facing down, and then you attach to your interposer or your substrate. Okay. So this is still used today for the mainstream, no matter it's your GPU, CPU, whatever. So from the package point of view, you need to cool down this processor, right? Think about this high performance CPU, GPU, you have a few 100-watt power consumption. So what is done there is to, you have some materials attached to the silicon bulk as a heat sink. You have this thermal interfacial material and then attached to the bulk of the silicon. So silicon bulk is quite conductive in terms of the thermal conductivity. So you generate the heat from your transistor here, and then the heat will go this way. And then you may have your air cooling or liquid cooling, whatever cooling here. So you have air fan or whatever. Then the heat will go this way, okay. But now, if you have the backside power delivery, then the situation will change. So here now the die is facing up. Why is that? Because your power always comes from the package, right? From the package. This is your power. So then you have to make the die facing up. First of all, the die is thin down, right? Now you only have a few micrometer thick silicon. And then you have your backside power delivery, PDN here. And you have the power in. And then this will be your transistor, right? And then we have the nano TSV connecting this. This will be your transistor, okay? And then you have the signal routing and the regular BEOL. So basically the die is facing up. Now you do not have the bulk of the silicon to dissipate the heat. So your heat is generated somewhere in the middle here in the silicon transistor. So here, that's why it's proposed to add this like another silicon carrier wafer here. So you add some wafer, like a dummy wafer or carrier wafer to attach to this BUL, and then you have your heat sink. So still, this is not as effective as this one, because now the heat needs to first go through this BUL, which is like 10 layers of metal and dielectric, the mixed material between the metal and dielectric. And then you go to this carrier wafer, and then you go cross. So this is still under research. There's no final solution here. How do they get? Okay, so still some of TSV, you for this I/O, you still need to go through the. Let's say you have some TSV for the power, some TSV for the I/O. But those are not many, right? Your I/O pin, tens of 100 I/O pins, that's it, right? And then the routing, is for their internal connections, the signal or clock or whatever. Those are generated internally, right, on chip. Okay. So here is a roadmap, right? Transistor evolution, planar NMOS, PMOS, right? And then share the gate, it's like inverter. And then move to the FinFET. And then gate around nanosheet 23. At least Samsung has this in their 3nm node. And then the future, okay, is to stack NMOS on top of PMOS in this nanosheet fashion. So this is called CFET, complementary FET, because N is on top of P. So this is complementary, okay? This is still under research, not in production. So let's show you something. If the CFET becomes available, then that will greatly help with SRAM cell design, because now you can stack the NMOS on top of PMOS or PMOS on top of NMOS. I mean, it's not finalized yet, but the industry prefer NMOS on top of PMOS at this moment. So you can further shrink the SRAM cell size, right? Because you have NMOS and PMOS. If one of them could be on top, then you will reduce, for example, here, like 40% area. So still, as there's some space for the scaling, if you take advantage of the third dimension. So here are some demonstrations to show that NMOS on top of PMOS, like four layers, stack nanosheet, NMOS on top of PMOS. And if you look at the last year's IEDM conference, both Intel and TSMC had a paper on this NMOS stacked on top of PMOS. At least they have some demonstrations in this technology. So it's on the roadmap, and I'm pretty sure industry will go to this point in like maybe 8 years or 10 years from now. This is for this so-called A5 technology node, 5 angstrom technology node. But as you know, nothing here is 5 angstrom. Okay, just equivalently, let's say, we're going to extend the technology. Okay, so let's revisit the variability again. So here, as we shrink the technology node, then the different sources of the variation will change. For example, we talk about the RDF used to dominate the process variation in the bulk planar MOSFETs. Then this impact decreases. But then the high metal gate introduces the work function variation. Right, this geometry is like this LER stuff, then kick in. Especially for the FinFET, then this will become, as you narrow the fin and also make the fin higher and higher, then this geometry effect will play more and more important role. So for the future, the GAA, we don't know. There is a hope that the GAA will help in terms of the variations. But this still needs to be, measured in the statistically in the large volume. So I just want to emphasize a few more tricks to extend the scaling moving forward. Actually, the DTCO has been already used for the last few generations to effectively reduce the cell size or increase the integration density. So what is DTCO? It's design technological optimization. Especially, it is about how to play with the transistor characteristics and the layout effects. Okay, how to optimize those design rule, and then how to incorporate with the technology features So here, this was a talk given by the TSMC, a chairman at that time. So here you see that at least in TSMC's process, the improvement in recent node really come from the DTCO instead of the intrinsic scaling. Intrinsic scaling means you just reduce the dimensions of the transistor or the spacing between transistor. So DTCO help, okay? Intrinsic scaling here is that you just shrink everything. But shrink everything will not help you because it's very difficult to, maintain those at small dimensions. So DTCO here, for example, one example here is the contact, okay? The contact to the gate, this is FinFET design, right? As source and drain, and then you have the gates in between. So the gate contact used to be here, outside the fins, So the gate contact will take the space. And in the new generations, there is a contact on top of the active region. If you can do the contact here, then you save the space. So this is one example of the DTCO. It's related to the design rules, but it also is related to the technology, whether you can do this contact fabrication on top of the fin.
Is that the area improvement or is that the performance improvement?
So mostly here, the area improvement, but later you'll see that some of those DTCO will also help with the performance. So here, for example. So here, the first example is from Intel. I believe Intel 4 process, Intel 4 nanometer process. So here it has reduced the diffusion gap or diffusion spacing between the N and P region. So you have like a narrower spacing between N and P or diffusion break. So that will help, okay? And also this contact on top of fin will help, right? And also the fin depopulation happens. So used to be 4 fin in the 7 nanometer process for NMOS and PMOS, right? 4 fin, you see. Now in the 4 nanometer, only 3 fin. So why is that? Because as we discussed earlier, each fin become taller. Each fin will give you more current. So previously you need 4 fin to give you, for example, 1 million. Now you only need a 3 fin, okay? So that will help. So this is all about DTCO. And also TSMC introduced this fin flex in their, I think, 3 nanometer process. So that is to make the standard cell design more flexible. Previously, you must have 3 NMOS fin, 3 PMOS fin. Now they can, mix and match. You can have 3 NMOS fin, 2 PMOS fin, or something like that. So that can make it flexible in terms of the standard cell design. This will give you a wider range of the design options. So you see from the 5 nanometer to 3 nanometer, if you do this like flex fin kind of layout design, then you can have the high performance or low power or high density designs. So it's an interplay between the technology and the design. So any questions here? Okay, so then DTCO flow. So this is a presentation from Synopsys. So the DTCO, you need to understand the transistor characteristics, the fabrication, and then you can do this TCAD simulation and then build the transistor model in TCAD and extract the parasitics, and then build the transistor models. And then you generate the standard cell, neighbor cell, and then in the layout. And then you consider the routing in between. And then you plug in everything into the digital design flow from the synthesis to the placement and route. So you can do this predictive design using this kind of flow. And even nowadays, people are talking about the STCO, system technological optimization. On top of DTCO, then they add the package level design consideration and also the 3D-IC design flow to really consider that the thermal, the power delivery, all kinds of issues on top of the performance and area. So this has become very complicated, but this is what industry is, innovating these days. All right, so then the last slide before we move on. So the SRAM we mentioned before has entered the 3D V-cache era. This was pioneered by AMD with the TSMC technology. So let's revisit the Zen 3 architecture. And it has 64 megabytes L3 cache, they call L3 extension cache, which is this part, bounded. Okay, this is the top die and the bottom die, bounded with the core here. So on the core, it has 32 megabytes L3 cache. Okay, in total, it has 96 megabytes. Both 3D, let's say the top die is in 7 nanometer and the bottom die is in 7 nanometer. And then they have some structural die to, provide the mechanical support and also probably function as a heat sink. So in the latest Zen 4 architecture, not much changes. The only difference is that the core, the bottom die, is implemented in 5 nanometer, but still the top die is 7 nanometer pure SRAM cache. Okay. So here, this is a summary for the SRAM lecture. So SRAM compatible with the CMOS logic process. Of course, the design rule may be a little different, but then the transistor itself is the same as a logic transistor. If it's FinFET, then SRAM is also FinFET. And then the variability, soft error, those are critical for the SRAM. So here, the future trend, as I said, DTCO will play more and more important role. And we will see the transition from FinFET to the stack nanosheet very soon. At least Samsung already has that in 3 nanometer process. And then the 3D bonding, right? Multiple SRAM dies stacking is also a compelling approach. So those will help with the extension of the scaling, at least in the next decade. All right, any questions before we stop here? Okay.